So, welcome to today's second session. And today's second session is on link budget analysis on 5G. And this session will be taken by Dr. Prashant Kumar. Let me unmute all. Let me mute all. So Dr. Prashant Kumar is accomplished associate professor at NIT Jamshedpur, bringing over 19 years of expertise in both undergraduate and postgraduate education. His academic journey began with a BSc Engineering in Electronics and Communication Engineering from Bihar College of Engineering, Patna, now NIT Patna, in 2002. He furthered his studies with an MTech in Telecom Engineering from NIT Durgapur in 2007, followed by PhD from IIT Patna in 2016. His extensive research contributions are evident by numerous peer-reviewed papers in esteemed journals and conference proceedings. Dr. Kumar's research and interest encompass a diverse array of topics, including wireless communication, underwater sensor networks, device-to-device communication, FPGA prototype development, and microscale energy harvesting. Presently, he serves as an assistant professor in the Department of Electronics and Communication Engineering at NIT Jamshedpur, India, where he imparts his wealth of knowledge to aspiring engineers. Dr. Kumar is not only dedicated to academia, but also holds significant membership, including senior IEEE member and life membership in IETE and ISTE New Delhi. Moreover, he holds the prestigious role of principal investigator for two sponsored research projects focusing on underwater communication, highlighting his leadership and expertise in his specialized field. With this short bio, I invite Dr. Prashant Kumar to take this session on 5G link budget analysis on 5G. Dr. Prashant Kumar, please go ahead.
Thank you, sir, for such a nice introduction. So good morning to all the participants. I think my slide is visible and I am clearly audible.
Yes, sir.
Yeah. Okay. So today we are going to talk about power link budget analysis of 5G. And all of you are very much aware that we hold the mobile phones, and there's a very critical issue that whenever we are on the journey or whenever we move, sometimes we find that we get disconnected. Or suppose you're walking and all the way you enter into the corridor, or you go on the staircase, or you go in the lift, you see that your network gets disconnected. So all of us think, what is the reason behind that? And all of us intuitively know it also. We know that when we reach a location where the signal strength is very weak, we get disconnected. And this is one of the things that all of us think, and we also think, why don't the telecom companies increase the power strength so that the signal can penetrate wherever we go? So based on these things, I have been using the phone for almost now 20 years. And I myself have experienced so many things, and initially those things were just factual. Then I tried to find out what is the reason behind that. And in that process, I came across several experiences that I'll share in the this session right now. I think all of you must find it very interesting, and you will also realize that there are certain things which are to be taken as myth, and certain things which are to be taken as reality, and we have to take advantage of this knowledge. So this is the outline of my talk. I will discuss about 5G networks and RF radiation. Then I will talk about the losses and gains in the link budget. I'll talk about the receiver sensitivity. I'll take an example and discuss a generic link budget so that you can perform some kind of calculation on your own. I'll talk about the propagation models for link budget. Then I will discuss about scenarios for link budget. We'll talk in particular about some of the scenarios like UMI, Street Canyon, which is also known as Street Canyon model, or UMA, We'll discuss about these type of different scenarios in the upcoming slides. Then we'll also focus on what is the real arithmetic behind the budget calculation. And finally, I'll also talk a little bit about the antenna modeling concerned with power link budget. Okay. So I'll give a very brief introduction because this is a fresh session. So let us begin with talking about 5G first for a minute or two. What is 5G communication network? All of us are now very much aware. The fifth generation mobile network is a new global wireless standard, and it comes on top of the 4G. We are said to be enjoying the 4G because when 4G network came, a major change occurred, and we were able to have very good quality of data network and access. The 5G enables a new kind of network that is designed to connect virtually. See the terms everyone and everything together, including machines, objects, and devices. They offer significant improvement in terms of speed, latency, capacity, connectivity compared to previous generations. However, realizing the full potential of 5G will require continued investment, collaboration among stakeholders, and ongoing research and development. And an FTP like this, what we are right now participating in, is a very good step in this direction. The features of 5G network. I've taken this picture from one of the sources which have been cited in the reference. This basically talks about three different domains of 5G. One is the massive Internet of Things, mission critical control, and the other is enhanced mobile broadband. As you can see, the 5G network has features like deep coverage, strong security, which is very much important for things like health and government finance, trust, etc. Ultra high reliability with a very low bit error rate, and ultra low latency, very fast access, extreme user mobility. That means even if you are in a bullet train with a speed of 500 km/h, you should have the connectivity. Then deep awareness, that is discovery and optimization. That means even if you are in a very weak critical condition, then also you can access the network. Extreme data rates in terms of Gbps, extreme capacity in terms of coverage area, having high uplink and downlink data rate, which is possible. Like an example is 10 terabytes per kilometer square. Ultra high density, 1 million nodes per kilometer square. This not only includes the human being as the user, this includes all the machines, the IoT objects, and other things. Ultra low complexity. We want 10 seconds of bit per second. This is a very ultra low complexity, so that there is little heating in the processing unit concerned. Ultra low energy. That is, we want 10 plus years of battery life. So these are some of the features which have been focused by different 5G companies which have come up, and they are trying to comply with the standards predicted in advance. The different components of 5G network include the user equipment, the handheld devices that we have, the laptops, tablets, and IoT devices and other connected devices. The second, the most important, is the the radio access network, which is RAN. It connects the user equipment to the core network and providing wireless access to 5G services. The GNB, that is the base station in our case, communicate with UIs, the user equipment, using new radio NR air interface, and supports beamforming, massive MIMO, and dynamic spectrum sharing. These are very important terms. We'll open these terms as we move ahead in the presentation. The core network facilities are service management function for allocating IP addresses and providing connectivity to external services. Access and mobility management for user authentication, mobility management, and handover. User plane functions for routing user data packets. Session management functions for establishing, modifying, and termination of user sessions. Policy control functions for enforcing policy rules and quality of service policies. Dynamically adjusting resources. Transport network, physical infrastructure for carrying data traffic between base station and core network. The network function, virtualization, and software-defined networking, enabling virtualization and programmability of network functions. Operators to deploy and manage network services. Management and orchestrations, MANO, provides the management and orchestration of virtualized network functions and network services, OSS BSS system, management and operation of 5G network, including network monitoring, fault management, performance management, billing, and customer management. These components, they work together and they enable a wide range of services and applications, including the enhanced mobile broadband, ultra reliable low latency communication, and massive machine type communication. The earlier sessions we have already gone through these things. Is just a kind of refresh. Now what concerns the power link budget and why we are here to discuss the power link budget is a very interesting fact. Earlier, the 4G networks, 2G and 3G networks, they had antennas which were relatively simpler, and they were single antennas beginning from first generation and gradually moving towards 4G. What we have seen there, the connectivity issues were there, but the problem was that there was one or two path link with the user equipment and the base station. And that was also responsible for lack of connectivity in remote areas and poor signal strength at different locations where there used to be some kind of shadowing and other things. But in the new technology, this is the 5G, we are using an adaptive system. An adaptive system, it is like the transmitter, the base station can search the equipment and send dedicated pointing beams towards that. But this is a matter of concern because we are now exposed to a set of beams. Our phones are pointing beams directly towards the base station or wherever they can. There's a point that we need to consider here. We'll just go ahead and see this. The 5G and radiation, RF radiation, there are certain myths and reality. Based on the diagram I have shown here, we can see that earlier there was a single link between the user equipment and the base station. And I would also like to tell you that there's a point to note here that the signal that reaches you when you are indoors through multipath, and that is a combination of signal coming through reflections from different objects. Whereas when you are in the outdoor, you get a direct line of sight communication, and those signals are strong compared to the multipath that we receive indoor. So there is an article which was written by Blake Levitt, and he wrote it in 1995, and then it talks about a very absurd type of thing, although somewhat reality. 5G, it says from blanket to bullets. So what is the meaning of blanket? Earlier it says that we were exposed to a blanket of electromagnetic radiation. It was thick and it was less dense. But now we are exposed to bullets of electromagnetic radiations. So what is the myth and the reality? Let us discuss. Phased array will transform the blanket of radiation which has enveloped our world for 2 decades into millions of powerful beams whizzing by us at all times. Antennas will concentrate their energy into narrow, steerable, high-power beams. The arrays are going to track each other so that wherever you are, a beam from your smartphone is going to be aimed directly to the base station and vice versa. Even if you are standing near a user or if you are in a crowd, multiple beams will overlap and be unavoidable. 5G phones can radiate a maximum of 2 watt, generally less than a watt. So now, based on these, the FCC has also issued some guidelines. Like there's a guideline that you should have a metal shield between display side to protect from this kind of radiation. We want the head of the user to be protected from the radiation of the antenna coming out and pointing towards the base station. So that put a guideline that you should put a metal shield so that when a person is talking, the radiation should not go towards his head. But this is not always true, because suppose when you are talking holding a phone, the person who is close to you, he or she is exposed. So this is a concern, and this forced me to think, how do we calculate the power? Why don't we increase the power beyond a certain value? And what is the acceptable level of radiation? So based on these things, we will study the power link budget and try to understand what are the restrictions and how to overcome these hurdles. What the standards say? A 5G cell site takes just 15% of energy of a 4G cell site to transmit the same data. So this is a good news. A faster transition to 5G globally could save 0.5 billion tons of carbon dioxide by 2030. Although the maximum radiated power in 5G is higher than that of 4G, the radiation intensity is 25% of the maximum exposure for 95% of the cases. So these are all good news. 5G, like 4G, is well within the non-ionizing zone. Energy not enough to break DNA bonds and are considered safe. Low power minimizes exposure. We are constantly surrounded by electromagnetic energy. Path loss models, path loss propagation model, will help us understand the reason behind this kind of exposure. Let us now talk about these things. So path loss propagation model is an experimental mathematical formula for characterizing the propagation of radio waves as a distance function between the antenna of transmitter and receiver. These models are designed based on a large data set collected for a specific environment. 5G will use Advanced Antenna System (AAS), a mixture of Advanced Antenna System radio and a set of Advanced Antenna System features. So the AAS includes multi-antenna technique, namely beamforming and MIMO. All bands in 5G need antenna system to support them. Thus, the 4X antennas are mandatory for 5G core bands. And this, to some extent, justify this diagram. As you can see, that there is a beam of electromagnetic radiation pointing towards the devices. We'll just clarify these issues. So there's an article again by Dr. Gerald Busberg, and what he says is that there are different wireless equipments that all of us use, like the Bluetooth headset, small cell towers, cordless phone. These expose the human being and all the biological environmental things to electromagnetic waves. So the light, if you consider light, the sunlight or normal light, the light produced by a light bulb is a form of electromagnetic radiation with energy and frequency that is approximately 17,000 times greater than that of highest frequency used by 5G. So are we getting endangered by the light of the sun or the light of the bulb? So he has given some conclusive points. These are called the key takeaways in his article, and he says, studies show that cellular signal, including 5G, are safe. 5G is the next generation of cellular network and builds on 4G. 5G emissions are similar to those from everyday technologies like TV, radio, Wi-Fi, even your toast. So it's not a matter to worry a lot. Now we'll focus now on the link budget for 5G communication. And a generic link budget for 5G communication involves calculating the gain and losses encountered by a radio signal as it travels from the transmitter to the receiver. While specific link budget may vary depending on factors such as frequency band, deployment scenario, and system requirements. So we'll one by one take up the transmitter side, the channel part, and then the receiver part, and try to formulate how to do all these calculations and how the telecom companies do these calculations, and they make sure that there is full connectivity. So the transmit power, PTX, let us assume a typical transmit power level such as 30 dBm, which is equivalent to 1 watt. The transmitter antenna gain, GTX, consider the gain of a transmitter antenna, for example, 5 dBm, free space path loss. Let us say the distance is D. The distance between the transmitter antenna and the receiver antenna is 1 kilometer. Let us say the frequency F, the operating frequency is 3.5 gigahertz. Free space path loss model. So free space path loss can be calculated using the Frisch transmission equation given below, which is F free space path loss in dB is 20 times log 10 of D, the distance, and 20 times log 10 of frequency minus 147.55. So using the data that are provided for the transmitter in this case, the free space path loss will be approximately 103 dB. Now the propagation losses. Additional path loss due to propagation effects such as atmospheric absorption, terrain, and building penetration may occur.
Excuse me, sir.
Yes.
Can you please show the equation for a moment? Previous slide.
Yeah.
Thank you. Just I am noting that.
Yeah. Actually, the log 10 it should have been in the subscript. You can check it. It should have been in subscript, but yes, there's some problem. The log 10 should be in subscript. Okay.
Okay, and this 147.55 is a constant, which needs
We will
to be
discuss it. Yeah, it is a constant in the present case. We'll discuss how it is achieved, and we'll just talk about in the next few slides. Right.
Okay, thank you.
Okay. So now the receiver side. So receiver antenna gain is GRX. Consider the gain of the receiver antenna, for example, 5 dBi. Then the receiver sensitivity. Assume a receiver sensitivity level to be such as minus 100 dBi. Now here I would stop and I would just remind you all about what you have read in electronics and communication engineering. When we talk about receiver, like all our phone, our radio, television, they are basically receivers. Okay, and when you do the transmission, it becomes transceiver. So all the receivers, like our phone, they have three very important characteristic features or properties, intrinsic properties. These are terms like sensitivity, selectivity, and fidelity. So we'll discuss these terms, although we are more concerned with sensitivity. So we'll define it again and again in the ongoing slides. We'll first talk about what is selectivity. So selectivity is the ability of a receiver, like a phone, to only receive the frequency component it is supposed to and reject all others. For example, if you have a 3G phone, it should only receive the 3G frequencies allocated to it and not be concerned with other frequencies. So it is selective. And the second term is sensitivity. Sensitivity is the ability of a receiver to receive and amplify the weakest signal. So every receiver comes with a minimum value that it will work only when it receives this much amount of energy, this much amount of radiation strength. So that is the sensitivity of the receiver. And if the signal strength is lower than that, then your receiver will fail to work. And this is what happens in the normal mobile phone. When you go to some basement or you enter into some very indoor location where the signal strength is very weak, the signal strength may go below the sensitivity level of the receiver, and in that case, communication will not be possible. This is a common day experience. We all experience. Suppose you go into a lift which is generally surrounded by a metallic sheet, so your phone will not work because the received signal strength becomes very weak, it goes below the sensitivity of your phone. Okay. And the third thing is the fidelity. Fidelity basically means when you are communicating, the range of signal that you are receiving, that is the message signal, the output level should not change with respect to that. That means whether you are listening a song on your phone or whether you are talking to your friend on your phone, the quality of output should not change. Then we say that the receiver is very fidel. So we have three terms I have explained: sensitivity, selectivity, and fidelity. Well, right now we are talking about sensitivity. So in the present case, let us say the sensitivity of your phone is minus 100 dBm. So total gain. So total antenna gain, if we sum up the antenna of the transmit side and the receive side, now right now in my example, it will be 10 dBi. So let us now talk of the link budget, which decisive calculation, that whether the signal strength that you are receiving, in that case, whether your receiver or your handset will work or not. So if you calculate the received power, calculate the received power at the receiver using the link budget equation that is given below. We'll talk about these equations again and again. So PRX in dBm will be P transmit in dBm plus gain of the transmit antenna in dBi minus free space path loss in dB plus gain of the receive antenna in dBi and we have to subtract some additional path loss. We'll talk about this in the later slides. So the PRX in my case will be minus 63 dB. Compare the received power to the receiver sensitivity to determine if the received signal is above the minimum threshold for the reliable communication. In this example, the received signal strength is minus 63 dBm, which is more than the minus 100 dBm sensitivity of the receiver we have discussed in the previous slide, which indicates that communication is feasible. But imagine that you are in such a situation that the received signal strength is minus 63 dBm, your sensitivity is minus 100 dBm, and taking the phone while you are talking, if you enter into the lift, what will happen? The received signal strength will not naturally go below the sensitivity level, and at that time the connectivity will be stopped, and then communication will not be feasible. Other link budget factors. Actual link budget for specific deployment may incorporate additional factors such as antenna diversity, fading margin, interference levels, and system requirements to ensure reliable and efficient communication. We have to consider some margins. For example, suppose you are talking and all of a sudden bus comes in between you and the base station. So naturally, for a time being, for a small period of time, the signal strength may go down. So if you are working neck to neck, in that case, the connectivity will break. So we have to always consider some margin. This may be due to shadowing or some other reasons. So whenever we do the link calculation, we always take something more than the minimum, and we incorporate these margins. We'll talk about this in the coming slides. Radio propagation scenarios. Now, whenever the telecom operator, they approach a place and want to have established a telecommunication network, they have to analyze the place where they're going to set up the network. And for that, they consider the propagation scenarios. And in the 5G standards, the propagation scenarios have been very specifically defined. Although they are not hard and fast rules, but they have been obtained by research, and these are standard, let us say, standard models that you can consider while you are designing a network or a cellular network in a particular demographic region. So first we'll talk about what is the UMI street canyon model. UMI stands for urban micro scale. Okay, urban micro street canyon model. Then UMA urban macro, RMA is rural macro, RMI is rural micro, INF is in factory. That can be in office also in 5G communication. In the context of 5G communication, these refer to different type of radio propagation environments or scenarios. These scenarios are defined by the characteristics of the surrounding environment, such as urban, suburban, rural, and indoor environments. Each scenario has distinct propagation characteristics that influence the design and performance of 5G network. So we'll take them one by one. The urban micro refers to the microcell environment, typically characterized by densely populated urban areas like in metro cities, with tall buildings and narrow streets. In here, let us not consider narrow street as a very narrow street. Narrow street means a normal type of street where people will move and it will be surrounded by high walls. In UMI scenario, signal propagation is heavily influenced by buildings, resulting in high level of shadowing, multipath propagation, and signal attenuation. To mitigate these effects, 5G network in UMI environments may utilize small cells, massive MIMO antennas, beamforming, and advanced interference management techniques. This is an example. In the diagram, you can see the urban micro or the street canyon, and you may understand why it is called a street canyon. Canyon, you know, is a barrel type of thing. So it is street canyon model. In the same way, in the other side, you can see in the open area. So these are two diagrams that depict the street canyon model and the UMI open area model. These are the sources are mentioned. Now, the urban macro scenario represents the urban macro cell environment, which include less densely populated urban areas with wider streets and lower building density compared to UMI. So normal town. In UMA scenario, signal propagation is affected by both building structures and open space, leading to a combination of shadowing, multipath propagation, and line of sight. 5G networks in UM environment may deploy macro cells, bigger cells with higher transmit powers, beamforming and adaptive modulation coding schemes to optimize coverage and capacity. It may be kept in mind that whenever telecom company or operator operates, its target is to provide very good coverage and high capacity. This is an example of urban macro. You can see here the antennas are put at a greater height, and they have more powerful transmitters. Rural macro scenario represents rural macro cells environment, which include sparsely populated rural area like villages with relatively flat terrain and few obstacles. In rural macro scenario, signal propagation is primarily influenced by terrain, features, and vegetation, resulting in lower level of shadowing and multipath propagation compared to urban environments. 5G networks in rural macro environment may utilize macro cells with higher antenna heights and lower frequencies to achieve wider coverage and penetration obstacle more effectively. This is the rural scenario. As you can see in the right side, you can see small houses in a circular cell with single base station. Whereas you can see on the other side, left side, you can see there can be things like balloon type of transmitter, which can use the radio link of service provider. Then there can be radio link, optical link, and different options are there. This comes under the category of service and network orchestrations or the man. Okay. Now in the rural micro scenario, include small rural communities or areas with dispersed population clusters. In rural micro scenario, signal propagation characteristic may vary depending on local terrain and vegetation, but typically exhibit similar features to RMA scenarios with less extreme variation in signal strength. So let us think of a situation where there is a hill or a dense, very low populated area where few people live and small pockets. So in that case, we call it as a rural micro. And we have to provide service to all the users. The 5G network in rural micro environment may employ a combination of macro cells and small cells to provide coverage in area with varying population densities and terrain conditions. Terrain means it may be a plateau or a hilly area or some valley type of feature. Now the indoor factory or indoor office. This is a very interesting one because most of the time when we enter into a shopping mall or a very big factory, we find that the connectivity is very poor. In that case, suppose you enter into a mall, maybe when you are shopping, you find that the signal strength is weak. You may not receive any WhatsApp message, or you might have noticed that the counters in the shopping malls, they are very close to the entrance point. One of the reasons is that now people want to use internet to make payments, to find certain things. So the indoor environment is a very interesting one. In indoor or in factory scenario, this represents the indoor environment such as office, shopping malls, airports, and stadiums. In indoor scenario, signal propagation is heavily influenced by building structures, materials, and indoor obstacles, resulting in significant signal attenuation, multipath propagation, and interference. 5G network in indoor environment may utilize indoor small cells, distributed antenna system, and advanced indoor coverage solutions to provide reliable and high capacity connectivity. This is an example. In the diagram you can see in the indoor environment, you have to manage some small picocell type of thing. Otherwise, the people who will be inside the office or the building may not get wireless connectivity. Now again, let us think about the link budget design consideration. Understanding these different propagation scenarios is essential for designing and optimizing 5G network to meet the diverse requirements of various deployment environments, ensuring efficient use of spectrum, maximizing coverage, and delivering high quality service to users. Propagation models for link budget for 5G communication. Now, we are now more interested in the free space model. We have already discussed the scenarios. Now we talk a little bit about the free space model. Remember, when we are talking about normal light communication, like the sunlight, if you are moving in open field, we remember that we used to follow the inverse square law. But with mobile communication, we have multipath. And in multipath, we have to consider certain free space propagation models. So we'll just take up some of the standard empirical models and then we'll come back to our link budget calculation again. In 5G communication, various propagation models are used to estimate the path loss between the transmitter and the receiver, which is a major component of the loss, which is essential for calculating the link budget. These models take into account factors such as distance, frequency, environment, and terrain to predict signal attenuation and enable the design and optimization of wireless networks. So first we'll talk about the free space path loss model. The free space path loss model is a basic propagation model that assumes ideal condition with no obstacle or reflections between the transmitter and the receiver. It is based on inverse square law and calculates path loss as a function of distance as well as frequency. Then we have the log distance path loss model. The log distance path loss model extends the free space path loss model to include additional factors such as path loss, exponent, and reference distance. Mind it, the reference distance. The Hatta model is an empirical propagation model commonly used for urban and suburban environments. It considers factors such as frequency, distance, and base station antenna height to estimate path loss. So this is in fact the first model that takes into account so many things like the base station height and the user equipment height, and it considers multi-path propagation. Then we have got the Okamura-Hatta model. The Okamura-Hatta model is an extension of Hatta model that incorporates additional parameters such as mobile terminal height, base station antenna height, and correction factor for different frequency bands and terrain types. It is widely used for predicting path loss in urban and suburban environments. Now, I may like to tell you that basically they have given very big empirical equations. I'm not showing those equations. Those who have gone through courses of wireless communication, they have already seen these equations. And these were the building blocks when wireless communication was growing up. These models were very effective and were widely used by the telecom operators to establish the cellular network and understand the power requirements. Then we have got the COS 231 wall face Aikigami model. Okay, the COS 231 231 wall face Aikigami model is a propagation model specifically developed for predicting path loss in urban and suburban environments. It takes into account parameters such as base station and mobile terminal heights, frequency, and distance to estimate path loss. I've told you that whatever power is transmitted by the base station, a major component of it is lost in the path loss. That is why path loss has to be studied, understood, and effectively used as a design parameter while setting up wireless communication networks. Then we have got the ITU, International Telecom Union, RP RP.14117 model. This model is recommended by the International Telecom Union for predicting path loss in urban, suburban, and rural environments. It incorporates a comprehensive set of parameters, including frequency, distance, building density, and clutter type to provide accurate path loss estimates. The choice of model depends on factors such as deployment scenario, frequency band, environmental condition, and accuracy requirements for the specific application. Additionally, advanced model may incorporate features as terrain data, building morphology, and statistical variations to improve prediction accuracy in diverse propagation environments. This is a comparative table which tells you about the different type of parameters which are considered. You can see the frequencies, mobile station antenna height, base station antenna height, distance between the base station and the user equipment, and the scope of application. You can see the different frequency ranges have been used in different experiments, and the different path loss models have been achieved at, and this has been achieved over different period of time. So they do not comply with each other as far as the specs are concerned. But these are all independent researches, and all of them have culminated to the present state of path loss model. Power calculation in 5G transmitters. So now let us again come back to incorporate what we have learned in the past few slides about the path loss. Calculating the power in a 5G transmitter involves several steps to ensure that transmitted signal meets the requirements for reliable communication while adhering to the regulatory guidelines and network specification. I told you earlier that whenever we have a call drop, we just curse the company that why can't they increase the power level? But truly speaking, the power level cannot be increased beyond a certain standard value, and there are regulatory guidelines which the telecom companies have to follow. So instead of increasing the power level at the transmit, they think about some other techniques. We'll talk about power calculation considerations. The 5G transmitters typically incorporate transmit power control mechanism to adjust the transmit power dynamically based on network conditions, channel quality, and signal to noise ratio. So I will tell you here a very interesting fact that when we people use the mobile phone, and if there is a call drop, we look at the signal strength. We have got an indicator in our mobile phone which shows some towers. Sometimes there may be 5 tower, 4 tower, or 1 tower, and sometimes no tower. Suppose when you are moving on train, you will find that you are not having any tower in your phone. So what is that? Basically, the mobile phone measures the signal strength. There is an equipment inside your mobile phone which takes help of the antenna and measures the signal strength. Okay, and it is indicated. If you go into the setting, you can see at any point of time you will be able to see what is the signal strength that your mobile phone is receiving. You can go into the system setup and see that. It may be in some dBm. So, like your mobile phone measures the signal strength and tells you that it is having good connectivity, poor connectivity, or normal connectivity. In the same way, at the base station and at the MTS, the mobile telecom switching center, each mobile phone user is also tracked. So there is an active table, and when you are registered to a particular MTS, your data is always there. So suppose you have good connectivity, the telecom company, with the help of that active table, know that you are in a good connectivity. Suppose you have poor connectivity, the telecom company knows that you have poor connectivity, and sometime when the connectivity breaks in the active table, you may be removed from the active table, and the telecom company may say, whenever someone makes a call to you, that this person is right now out of coverage area. That means in that case, the telecom company is measuring your signal strength because you are always sending some sort of handshake signal to the telecom company. It knows that the signal strength that it is receiving from a particular user is very low, and so it will remove that user from the active table and say that this user is right now out of network coverage. So you have to understand this. So the network companies use different type of transmit power control mechanism. The TPCs ensure that the transmitted signal power is optimized to achieve the desired coverage, capacity, and quality of service while minimizing interference and power consumption. There is a term maximum transmit power. The maximum transmit power, Pmax, is the highest power level that the transmitter can output under normal operating conditions. Pmax is specified by regulatory authorities and network operators to ensure compliance with safety regulations, spectrum allocation rules, and interference limits. Transmitters must not exceed the specified Pmax to avoid harmful interference to other users and devices. You may be aware that the government agencies, the TRAI, Telecom Regulatory Authority, and certain other authorities, they have to perform certain tests. They go to transmitters of different companies and monitor the power strength. And they check whether the particular company tower is complying with the rules or not, whether they are not going beyond a certain power level, which is granted to them. So the government agencies always do this type of test. Sometimes they put fines also on some private companies if they go beyond that power transmit level in order to provide high quality of service. It is not just a case of India. In different parts of the world, there are regulatory authorities and they do this kind of check. Sometimes they even ban the telecom operators just because they do not follow the safety regulations. Then the second one is effective isotropic radiated power, EIRP. It is a measure of power radiated from an antenna in a specific direction. It accounts for both the transmitter power and the antenna gain, providing an indication of the signal strength at the receiver. EIRP is often used to characterize the coverage, range, and performance of wireless communication systems, including 5G networks. Link budget analysis. Power calculation of 5G transmit involves performing a link budget analysis to determine the appropriate transmit power level for achieving reliable communication with the desired signal quality and coverage. The link budget considers factors such as path loss, antenna gain, receiver sensitivity, fading, and interference to calculate the minimum required transmit power of a given communication link. Power calculation considerations again. So dynamic power control. In addition to TPC, the transmit power control, 5G transmitter may employ dynamic power control techniques to adaptively adjust the transmit power in real time based on channel condition, user mobility, traffic load, and network condition. Dynamic power control helps optimize utilization of network resources, mitigate interference, and improve spectral efficiencies by adjusting the transmit power dynamically according to changing environmental and operational conditions. Regulatory compliance. This is very important. Power calculation in a 5G transmitter must comply with regulatory requirements governing electromagnetic radiation, spectrum usage, and interference mitigation. Regulatory bodies such as the FCC, Federal Communication Commission, in the United States and the European Telecom Standard Institute, ETSI in Europe, set limits on maximum transmit power, EIRP, and emission levels to ensure the safety and integrity of wireless communication systems. This is done keeping in view the environmental goodwill. In summary, the power calculation of 5G transmitter involves optimizing transmit power levels to achieve reliable communication while complying with regulatory requirements and network specifications. Transmit power control mechanism, link budget analysis, dynamic power control techniques, and regulatory compliance considerations are essential aspects of power management in 5G transmitters, ensuring efficient and effective operation of wireless networks. Power calculation in the receiver of 5G communication involves several key considerations aimed at optimizing the reception of transmitted signal and maximizing the reliability and performance of the communication system. Now we'll discuss on power calculation in the receiver of a 5G. By receiver of a 5G, there is a point that must be mentioned here. Like generally we think our phone is the receiver. So it's good, it is the receiver. But at the same time, we are also transmitting. So when we are transmitting, when my user equipment or my mobile phone is transmitting, there is a receiver at the base station also. So we have to consider the base station also as a receiver. And it is going to have a two-way communication. So the receiver at the handset and the receiver at the base station. And the transmitter at the handset and the transmitter at the base station, they have to both be considered. Signal detection and demodulation. The primary function of the receiver is to detect and demodulate the received signal to extract the transmitted data. Power calculations in the receiver begins with the reception of electromagnetic signal by the receiver antenna. The received signal power is characterized by metrics such as received signal strength indicator, RSSI. I told you about the tower indication, which measures the signal power level at the receiver. Receiver sensitivity, earlier also I discussed the very important thing. See, when we say that someone is very sensitive, we mean to say that even if there is a pin drop, that person will notice. So in the same way, by receiver sensitivity, we mean to say that a good receiver, let us take an example, it is not to be taken otherwise. If you buy a local company mobile phone and you compare it with a, let us say, an iPhone. So naturally, the iPhone is a very advanced system. It has got very high sensitivity. That means it can detect signals in when the signal strength is very weak. Then also it may work. But a local phone, which may be a low-cost phone, maybe, let us not take it otherwise, maybe it will not work even when an iPhone is working, because the sensitivity of the iPhone may be better than the local phone. Now, receiver sensitivity is a critical parameter that defines the minimum signal power required by the receiver to reliably detect and demodulate the transmitted signals. It represents the weakest signal level that the receiver can detect with a specified bit error rate or packet error rate. Receiver sensitivity is typically specified in terms of minimum received power in dBm or dBm microvolt required to achieve a desired level of performance. Here I would like to again emphasize what is the meaning of this bit error rate or packet error. Sometimes you may notice that your signal strength is weak. Still your receiver is working. You are able to talk to your friend, but the voice is cracking. What is the meaning of voice is cracking? Voice is cracking means that we are receiving the signal, but our receiver is not able to maintain the required bit error rate. That means that the received signal strength is fine. We are getting the signal, but the signal strength is not sufficient for the receiver to maintain a certain bit error rate. And in that case, the output is there, but it is very much erroneous. So because ones and zeros have changed, so when you reconvert back into analog signal and you produce a sound, the sound will not be of good quality. There will be cracking, there will be missing terms. So that is the meaning of bit error rate or packet error rate maintenance while we are receiving the signal. So receiver sensitivity is typically specified in terms of the minimum received signal power required to achieve a desired level of performance. Now, noise figure. Now, when we calculate the receiver sensitivity, we have some formula again. So we'll talk about some of the important terms, although these are maybe known to you. Noise figure and noise power. In addition to received signal power, the receiver also experiences noise generated by various sources, including thermal noise, amplifier noise, and interference from other signals. You know, noise is an integral part of all communication systems. It is always there, and we have to take care of this. We have to give due respect to noise and have to tackle this noise. Unless and until you take care of noise, you cannot have a successful communication system. So noise figure is a term. It is a measure of noise performance of the receiver and represents the additional noise power introduced by the receiver components. Power calculation in the receiver accounts for noise power to ensure that the received signal is distinguishable from noise and can be reliably detected and demodulated. Signal to noise ratio, SNR. SNR is again a very important factor and one of the critical factors in communication system. SNR is a key metric that characterizes the quality of the received signal relative to the noise level. You can think like this, that if you are talking to some of your friend who is just standing beside you, if you are talking in a quiet place, you can whisper and you can talk. But when you go into the marketplace, even if you shout, your friend is just beside you, you may not be able to communicate. Why? Because in the marketplace, the noise level is very high. And the noise level is much high compared to the signal level. Whereas in a silent place, the signal level is much high compared to the noise level. So SNR is a very important factor. It is not that by simply increasing the signal strength, you will be able to have communication. You have to have a trade-off. So it is the ratio, the signal to noise ratio that is very critical. SNR quantifies the ratio of the received signal power to the noise power and provides a measure of the signal clarity and reliability. Power calculation in the receiver involves optimizing SNR by maximizing the received signal power and minimizing noise power through techniques such as a low noise amplifier, filtering, and interference mitigation. Dynamic range. The dynamic range of a receiver represents the range of signal power level over which the receiver can operate reliably without saturation or overload. Power calculation in the receiver considers the dynamic range requirements to ensure that the receiver can accurately detect and demodulate signal across a wide range of signal power levels encountered in diverse operating conditions and environments. So I was talking about the cracking of voice. So when the cracking of voice is there, you are not getting good quality of service. Why that is there? Because either the noise power has increased or the signal power has decreased. So this may occur when you are moving in a train. Let us take an example of a train. In that case, the signal strength will naturally be less. Okay, there will be Doppler effect, and at the same time there may be noise. What is the meaning of noise? Noise is not just what we hear from our ears. The noise may be due to the movement, due to the friction between the wheel of the train and the track, due to the spark created by the power connector of the engine, and many other things. Maybe some kind of vibrations are taking place. So we have to take into account all these things, and these things are responsible of voice cracking when we are moving in a train, or due to some other things are also there. Automatic gain control. Now every receiver comes with this very unique feature. Automatic gain control is a feedback mechanism used in receivers to adjust the gain of the receiver amplifier dynamically based on the received signal power. AGC, automatic gain control, helps a constant output signal level at the receiver's output, compensating for variations in signal strength and preventing signal distortion or clipping. So if your phone has good AGC system, it will help you avoid voice cracking. It will have a better output condition. Power calculation in the receiver involves optimizing the AGC setting to maximize receiver sensitivity and dynamic range while minimizing the distortion and noise. Energy efficiency. Power calculation, the receiver also considers energy efficiency objectives to minimize power consumption and extend battery life in mobile devices, IoT sensors, and other receiver equipments. Techniques such as power gating, voltage scaling, and low power design are employed to optimize energy consumption and reduce the overall power requirements of the receiver. Overall power calculation in the receiver of 5G communication involves optimizing receiver sensitivity, SNR, dynamic range, and energy efficiency to ensure reliable signal detection and demodulation across a wide range of operating conditions and signal environment. I would like to point out again here that unlike the earlier systems of 1G, 2G, 3G, and 4G, the 5G uses a very wide bandwidth and wide spectrum. So it is very important that link budget calculation includes these considerations. Advanced receiver architecture, signal processing algorithms, and RF front-end design are employed to enhance receiver performance, coverage, and energy efficiency in 5G communication systems. This is a very simple diagram, and it tells you about where the power is lost. Like when we make the budget, we always consider that what we are going to earn and where we are going to spend. In the same way, in this diagram, you can see we are now doing a downlink budget in the cellular network calculation. So we start with the base station and the signal has to reach the user equipment. So starting with the top, you can see we have got the GNB, the transmitter base station. And just after that, there's a cable loss. We'll talk about all these losses one by one. There's a cable loss. Cable loss basically indicates that generally the antenna is mounted on top of the tower and the signals for the antenna are transmitted through cables. The cables run around maybe 35 meters or something like that. So there may be cable loss. In terms of electrical engineering, we say there's a feeder loss. That means we are feeding the antenna, there will be feeder loss. But sometimes the transmit equipment may be very close to that antenna. In that case, there may not be any cable loss. Or sometimes you are using, let us say, optical fiber. In that case, the loss will be negligible. Then the very first gain is at the antenna of the transmitter, it's GNB antenna. So it will be a kind of gain. This is a booster, a kind of booster. So you generate power, now you gain, provide a gain. Now there will be a path loss. I've told you the path loss is a very major component, major loss in the system. Then there is penetration loss. Penetration loss involves penetration into rooms, building walls, your clothes, your shields, your helmet, and different type of things. There is foliage loss. Foliage loss is the loss due to absorption of energy in the vegetation, the plants, trees, and other things. So we have to consider that when you are putting a network in any area, what is the condition of the foliage? How many trees are there? Maybe there is a dense population of trees. Suppose you are doing a planning of network in a forest, so in that or a forest region, in that case, the foliage loss will be very much measurable and very much quantifiable, major. Then there can be body block loss. Sometimes when we are talking, our body may come in between the phone and the transmitter. So there is body body block loss. There can be slow fading margin. Slow fading margin basically means that when for a small period of time something comes between the transmitter and the user. Like I gave you an example. Suppose a bus comes between transmitter and user for say 2 seconds. The signal strength may go down. In that case, we have to maintain a certain margin. That means we cannot move neck to neck. When you are making the budget in our houses also, we just don't do that expenditure should be equal to the earnings. So generally, we plan to earn more than the expenditure so that if there is any untoward accidental thing or any other thing, we have to take care of that. In the same way, fading margin and interference margin have to be taken into account. What is the interference margin? Interference margin is due to the interference from different operators or maybe from other cells. So there can be some kind of interference that will reduce the SNR value. So we have to account for that. We have to consider it as a margin. Sometimes there has to be rain margin or ice margin. Suppose you are in a rainy season, or what will happen? The raindrops may absorb certain amount of energy. So you have to consider the rain or ice margin. Ice margin, suppose there is snowfall or some kind of ice layer is on top of the building or on in the surroundings. Then we have to account for these margins. Then there's again a body loss. Body loss is actually the absorption of the body. First one was body block loss. This is now body absorption loss. Then the signal reaches the user equipment. So if the signal that reaches the user equipment is strong enough, let us say more than the user equipment reception sensitivity, then only the user equipment will show the towers in the mobile phone, and then only it will be able to function uh, as a receiver in receiving the signal, amplifying it and demodulating it, and then generating the required data. Now, when we do this calculation, as I've shown you this, you now remember the names. We are finding the link bucket signal at the receiver level. So this will be transmit power minus antenna gain at the transmit power plus antenna gain of the transmitter minus cable loss of the transmitter plus antenna gain of the receiver minus cable loss of the receiving side, and path loss due to propagation model, penetration loss, foliage loss, body loss, interference margin, minus rain or ice margin, then slow fading margin, penetration loss, indoor, and then attenuation indoor. When I say penetration loss, it is the absorption in the wall and other things, and attenuation loss is due to the different environment. See, the outdoor environment is different, the temperature is different, the temperature is different, but the indoor environment is different. So you can have penetration indoor as well as attenuation indoor. So all these things have to be taken into account. So basically, there are only three pluses. What is transmit power, antenna gain at the receiver, antenna gain at the transmitter. Generally, the antenna gain at the receiver is very low. So three pluses and all minuses. So the transmit power minus the part of the node B or the user equipment will give you the power used for data transmission. Now there is a path loss calculation. You can see this is I've taken from a source. I just mentioned the reference. You can see generally, first of all, we find a path loss reference. So for that we use lambda. Lambda or the frequency, lambda is the wavelength of the frequency we are going to operate, and d0 is the reference distance. So first we find the reference path loss. Then the path loss is equal to the reference path loss plus the n 10 log 10 d by d0 sf plus epsilon. What are these terms? You can see someone had asked me, so now you can pay attention here. The path loss is equal to the free space path loss at d0 plus the frequency dependent path loss exponent times 10 log 10 d by d0. D is the distance between transmitter receiver, and d0 is the free space reference distance, typically 1 meter. SF is the shadow factor, and epsilon is a random value with normal distribution. So now once you calculate this path loss, we find the power at the receive in dBm. This is equal to P transmit minus P path loss, that is the absolute path loss at a specified distance. What the standards say? Generally for 5G, we refer to one of the latest standard releases. It is the 3GPP TR 36.901 release 16. It is basically talking about the RAN frequency from random access network frequency. I'm sorry, radio access network frequency from 0.5, that is 5 megahertz to 100 gigahertz. Channel status, whether the signal at the receiver will be received or not, that is whether pass or fail, depends on the received power level at the user equipment and it receiver's sensitivity. So it is not just that you have to understand one more point here, that different people will have different user equipments. There are so many companies, they are making the mobile sets. Although all the companies are set to comply with the standards. So depending on the situation, like suppose you have to buy a car or a Jeep, you choose the one you need, okay, according to your requirement, because you know your requirement is all fixed. Maybe you are going from home to your office or going to some other place every day. So you buy a Jeep or a car or a SUV. But in case of mobile, basically mobile is a mobile equipment. You have to buy a mobile set. So when you buy a mobile set, do you actually check what is the receiver sensitivity? We never check it. General people don't check. So suppose you buy a phone, you generally see the camera, memory or processor, but we never bother about the receiver sensitivity. It is my sincere advice that whenever you go to buy a phone, you see the technical specification. And always see and buy those phones which have very, very low receiver sensitivity. Low receiver sensitivity means that those phones will be operational even if the signal strength is very weak. You might have noticed when you are moving on a train, your phone may not be working while maybe a person is close to you who has the same company SIM, his phone is working. It is just because that maybe the other person's receiver or the phone set is more sensitive. Okay, so based on the standards, the companies make the phones. They tell it also like that, but it's a matter of quality. If the phone's quality is good, the receiver sensitivity will be naturally very low. Now, PT, scenario and propagation. That is transmit power, the scenario of where you are going to use, and the propagation model decides whether communication is possible or not. Okay. Where is the power used? I told you earlier also we have feeder loss, which is negligible in case of OFC. Free space path loss, which depends on the model chosen. Slow fading margin, due to large obstruction, there can be shadow, which can have plus minus. We have to consider plus minus margin for that. Interference margin, this may come from other cells and other operators also. Foliage loss due to trees, rain and ice margin has to be considered because it is a condition that may occur anytime, and your system must take into account that it may rain any day and the system performance will not degrade. Power restrictions on base stations. Actually, this is a matter of concern, and all over the world there are different standards and different companies which follow different standards. When the people buy the base station equipment, they have to check these things. So for 2G and 3G, although I'm not very sure about this, just a standard I obtained from some non-technical document. For 2G and 3G, the base station transmit power is restricted to 43 dBm. 43 dBm is somewhat close to 20 watt. So you can think like this, that a base station of 2G or 3G mobile system is holding a bulb of 20 watt. It is not considered that it is generating visible light. It is things like this, that there is an antenna which is generating 20 watt of output power. It is similar to a 20 watt bulb if you think of light. Similarly, for 4G, it is 46 dBm, which is 40 watt. So a 4G base station transmits more power, in fact, double the power compared to a 2G or a 3G system. And similarly, for the 5G, it is 49 dBm, although it is not a matter of consensus. It is somewhere close to, let us say, below 50 dBm, and 50 dBm is 80 watt. So naturally, you can understand 20 watt bulb, 40 watt bulb, and 80 watt bulb. So the power level is increasing. That is why people are also concerned about the radiation level and effect of radiation, electromagnetic radiation on their health. And I would just also remind you what is dBm. So if you are measuring power, we use the dBm unit. It is X in dBm is equal to 10 log 10 power divided by 1 milliwatt. Okay. Signal propagation in cellular network is a very good example. I took it from source, is set in the reference. The tower is transmitting the signal, and in mobile communication, you may be indoor, you may be outdoor, and signal reaches you through multipath. So when the signal reaches you through multipath, it may hit a tree, it may hit a building, it may hit a glass pane, or it may directly also come to you. So this is a very good diagram that tells you what the signal propagation in cellular network. Typical loss values. So we have found these loss values in the document. Typical body loss frequency band. You consider for body loss, the frequency band is 3.5 gigahertz. Then it will be 28 and then in 3 to 5 it is 8 to 40. Of course, it is in dB. Typical body loss for 3 gigahertz is 15 dB. Then source 3GPP, I told you about the standard. For slow fading standard deviation, considering 95% coverage area, depending on the scenario, whether it is outdoor to indoor or outdoor to outdoor. For dense urban, one is 9, the other is 8. For urban, it is 8 and 7. For suburban, it is 7 and 6. You will find that outdoor to outdoor, the loss is less. For rural, it is 6 and 5, and for line of sight, it is 5 and 4. These values are used in the diagram I had shown you earlier. Let me just once again show you. This is the thing we are talking about. So depending on the scenario, these values will change. For example, foliage or pathology will change. So this is what I'm trying to show in this table. Similarly, a typical cable loss value, you can see in the diagram on the left, you can see sometimes you don't find the tower. You will find that the antenna is there and some cables are running to the lower part of the system. So the signal is sent to these antenna through cable. So this will account for a loss. This is called the cable loss. So if you have a radio and you have an antenna, suppose you are having a cable loss of 2 dBm, conducted power is 46 dBm. So antenna gain in this case, let's say it is 18 dBi. So you can find the effective isolated radiative power is 46 minus 2 plus 18, which is 62 dBm. This is how we account for the cable loss. Similarly, we have got other values like typical foliage loss for sparse tree. In case of 3.5 gigahertz, we have got 7.5, and in case of 20 it is 8. Dense tree 8.5 and 15. 2 tree, if there are 2 trees, then 11 and 19. 3 tree 19.5 and 4. Typical foliage loss 11 and 17. These values have been obtained by certain experimentations, and these have been accepted all over in the standards. Typical ice and rain margin for 3.5 gigahertz and 28 gigahertz 0 and 3. So depending on the frequency used, the losses generally differ. Typical margin values. Interference margin depends on the signal to interference plus noise ratio. For the 3.5 gigahertz, it is typical interference margin for downlink is 6, and for uplink it is 2, whereas for the 28 gigahertz, downlink is 1, and typical uplink margin is 0.5. Sorry. Role of path loss in cell design. Role of path loss in cell design. We consider GNB. GNB is the transmit system communicating with one UE, that is one transmitter, one user equipment over a 5G network. In an outdoor rural setting, to find out how the path loss vary with the distance between GNB and UE and their heights, perhaps a lower height is better for smaller sized cells. Perhaps a lower height is better for small size cells and a greater height is better for large cells. What is the trade-off? We have to think on that. This is an example. This is actually a formulation again cited from reference. You can see in this path loss calculation, how do we do? Let us consider a scenario of rural macro, and we consider either line of sight or non-line of sight. Let us first consider the line of sight. The path loss in dB for FC in gigahertz and D in meter is given by this formula. It is having, you can see path loss, rural macro LOS, then PL1, then PL2, we calculate it. And the shadowing factor sigma is considered. Parameter values range like HBS means height of base station, HUT means height of the user equipment. Okay, and similarly, W is the distance between, which is 20 meter, H is the 5, height is the 5 meter. You just take these things in a diagram just after this. Okay, so if the height is greater than 5 meter, then things change. If it is 1.5, if it is 5, if it is greater than 5, things change. So the formula also changes. Similarly, we have got path loss for the non-line of sight. In this case also, we have got one formula and the other formula, and for that the one of the component, that is the shadowing factor, is same, whereas the parameter values and the range differ. Here it is height of base station is greater than 10 meter and less than 150 meter, and in this case it is 1 meter. Height of user equipment is greater than 1 meter and less than 10 meters. So we use this formula. These are obtained by some experimentation, and these have been accepted as empirical formula for path loss. This is a very good diagram that tells you what is the role of the path loss. You can see on the left hand side, you can see that there is a transmitter, there is a hilly terrain. You can see if the first user close to the transmitter, it's good for it, you can receive. The second user is in shadow, third user is okay, fourth user is again in shadow, fifth user is also in shadow, but it is receiving some signal. Similarly, in the lower one, you can see if there is a water surface, then there will always be evaporation, and evaporation causes a lot of attenuation. So in the second case, you can see both the users are getting signal. In the third case, you can see that there is a big building. So the first user close to the tower is receiving signal. Second user inside the building is also receiving reasonably low signal. Third user, which is exactly behind the building in the shadow, is not receiving any signal. And the fourth and fifth and sixth, they are receiving signal proportionate to the distance and some other factors. Similarly, in the lower diagram, you can see on the left, the transmitter and the receiver which is close to the transmitter is receiving. But now, this time, the user which is behind the tree and the house is still receiving the signal because it is not a concrete building. Okay, so concrete structures have their own absorption. So in this case, the trees will not only absorb, they will also diffract the signals. So in that way, the multipath signal will be able to reach those users who are in the shadow also. Now, on the right side, you can see there is a topographical indication. Here you can see that there is a base station, and the first one, PR is greater than PS, means that the received signal strength is greater than sensitivity. PR is less than PS, and in the outside, the third one, where the signal strength is less, is not able to receive any signal. Now, cell radius and communication feasibility. Now, all of us know that we have studied this also, that initially when a company launches a network, they go for a big cell, then they gradually go on reducing the cell, not only to incorporate more number of users, but also to provide good quality of service. So what is the relationship between the cell radius and the communication feasibility? Communication feasibility means whether the mobile equipment will be able to work or not. Okay, and this is decided by the strength received at the user equipment. So in this diagram, this is also taken from one of the reference. In this diagram, you can see there is a base station, and HBS is the height of the base station. Then there is a user equipment, HUT is the height of the user equipment. Then the cell radius, this is D2D. It is the distance between the base station and the user equipment. Then, now again the same type of thing, conducted transmit radio power in dBm is generated. Then there is a feeder loss or a cable loss. Then antenna gain. So we reach a certain height. You can see on the right hand side, I am showing an arrow with power in dB. So when the distance is increased from the cell station, the base station, the signal strength goes on decrease. So where the losses are accounted, maximum path loss after margin, then body loss, penetration loss, shadowing interference margin, and ultimately what is reached at the UT is the antenna, and then there is antenna gain at the UT. So the signal is a little bit increased. And if it is more than the UT, that is a user terminal or user equipment receiver sensitivity, it's good. Otherwise, communication will not take place. That is, feasibility will not be there. Now, this is one scenario. Let us now talk about maximum allowable path loss. Link budget is used to determine the cell radius, or in other words, coverage area. By knowing the cell radius, we know how closely spaced cellular sites need to be. For instance, if we have 10 kilometer by 10 kilometer area, and if we determine that sites need to be located every 1 kilometer individual cell radius of 500 meters, we need approximately 100 sites to cover the entire. If, on the other hand, site needs to be located every 250 meters, we need approximately 1600 sites, which implies a much higher cost of network deployment. So from the network operator point of view, it is very important to consider these design considerations, that the network operator generally wants to install less number of base stations or sites. So how they can do it? So they can do it by taking into account all the losses and scenarios, and then they do and optimize how many sites are needed to cover the geographical region they are entitled to cover. We can start the 5G link budget exercise by first defining the link budget as a measure of maximum allowable path loss, MAPL, between the transmitter and the receiver, both in downlink and uplink direction. From the MAPL, and by making use of one of our path loss model introduced, we can determine the cell radius. This is a calculation. You can see there are two diagrams. One diagram is outdoor scenario and the other is indoor scenario. In indoor scenario, the path loss is split into two components. You can see there's a shaded box which shows that is in the indoor scenario. So there is a point known as the break point, which is a point in which before that, from the base station side, you are in the outdoor environment. After that, you are in the indoor environment. So if you look at the diagram, you will realize that D3D is now split into two parts, out and in. Okay, so using all the things that we have already considered, like speed of light and FC denotes the center frequency normalized by 1 GHz, all distance related values are normalized to 1 meter. Okay, so what we find that path loss equation for rural macro environment for LOS and NLOS, non-line of sight, are considered next. Okay, so you have to keep in mind that you are either in the open space outdoor or you are inside a building or a house. So we calculate the D3D out plus D3D in using the Pythagoras theorem, you can calculate. You will find this is given by the formula here, and this is a simple Pythagoras theorem. We are not doing any complicated calculation. Observing our equation, we see that the path loss is not a simple expression in terms of G and B height. The other parameters affecting the path loss are the UE, user equipment, and GNB 2D distance, and the user equipment state. Consequently, we have to consider how does the user equipment and the base station path loss vary for combination of GN height, UE and GN distance, and the UE state, whether LOS or non-LOS. This is a path loss value for various combinations. In this, you can see the height of the base station is varied from 10 meter to 150 meter, and the height of the user equipment is also changed. You can see when you change these things, you can see, I'm sorry, this is the distance. I'm sorry, not the height of UE 50 meter, and 500 meter. These are distance between the user equipment and the base station. So you can see the path loss varies, and the path loss generally in dB, it varies from 77 dB to 87 dB for 50 meter. Okay, and in case of non-line of sight, it is more, from 92 to 87. Again, similarly for 1 kilometer, for line of sight, it is 105 dB to 105.69 dB. So you can see the calculations can be done, and these values are used for designing a system while maintaining a certain quality of service. User equipment, or and I think ENG, receiver sensitivity level. Now we have to talk about the sensitivity once again. We talked about sensitivity in terms of the ability of a receiver to receive the weakest signal. Now, what are the important terms we have to consider on basis of which we can calculate the sensitivity of a receiver? So first we'll talk about receiver sensitivity. The reference sensitivity power level is the minimum mean power received. Yes? Do you have a question?
No, go ahead, sir.
So the reference sensitivity power level is the minimum mean power received at the antenna connector at which a throughput shall be greater than 75% of the maximum throughput for a specified reference measurement channel. The ability of a receiver to identify and amplify signals at the receiver input is called receiver sensitivity, and it is measured generally expressed in dBm. Now, a calculation is done here. See, the reference sensitivity is equal to the thermal noise, which is generally inside the receiver, plus noise figure, plus 10 times log of the bandwidth in hertz, plus SN. You have to keep in mind, this is a standard formula. It is also given in the reference. The thermal noise has a major influence on the quality of receiver. Low thermal noise means higher and more costly is the receiver sensitivity. Okay. Lower the thermal noise, higher and more costly is receiver sensitivity. What it means that if the thermal noise is low, you will get a better receiver. Thermal noise in a 50 ohm system at room temperature is minus 174 dBm. I remember someone has put a question from where you are getting the minus 174 dBm. So for a receiver, if you consider thermal noise in a 50 ohm system, 50 ohm basically indicates the impedance matching impedance value of the system with the antenna. Generally, we make electronic circuit and we have to match the impedance of the electronic circuit with the antenna. So thermal noise in a 50 ohm system at room temperature is minus 174 dBm per hertz. So the noise factor can be derived simply by taking the SNR at the input and dividing it by the SNR at the output. So first we find the noise factor, which is SNR at the input divided by SNR at the output. Then the noise figure is simply the comparison of the SNR at the input and output circuit expressed in dB. So noise figure and noise factor are figures of merit that indicate degradation of the signal to noise ratio that is caused by components in a signal change. So noise figure is the base station noise figure. NF is the base station noise figure. It can be 5 dB, 10 dB, or 13 dB for wide area base station, medium range base station, or local area base station. Required SNR means that minimum level of SNR required to decode the type of NR signal. NR signal could be of different code rates, modulation, etc. So for each type of signal, required SNR may vary. So a sample calculation for 100 megahertz and SNR of -1 is done here. So S, the reference sensitivity, has been calculated, and we are getting it as -95. And -95 dBm means, this is in dBm, of course, please pay attention. dBm means that it is having a good performance. That means the receiver will have a good performance. Let us now go ahead. So receiver sensitivity levels. Reference sensitivity is the most basic and important receiver requirement for mobile user equipment. More specifically, it is determined on the basis of taking the thermal noise at the baseline, taking into account UE demodulation threshold, UE receiver noise figure, and UE multi-antenna diversity gain, and then further reserving a certain implementation margin. The specific calculation formula is as follows. The reference sensitivity in dBm will be -174 plus 10 log 10 R into BW, that is the overall hertz of the system you are going to use. That will be decided by the numerology you are going to use for 5G, plus 10 log SU. Okay, SU is the spectrum utilization factor, and NF is the noise figure minus diversity gain plus SNR plus implementation margin. So I told you that we never go neck to neck, we always go with something in surplus. So in the above calculation formula, Rx bandwidth is the receiver bandwidth of the UE in hertz. Spectrum utilization is the full RB spectrum efficiency. Noise figure is related to the receiver noise figure for a given frequency band. Diversity gain is the diversity reception gain of the user equipment with two antennas. And SNR is the baseband demodulation threshold. So again, if you now do the same type of calculation using some standard values, for example, if you begin with a 5G system with having 49 dB, that is 80 watt of output power, 2 dB of cable loss, 17.5 dB of antenna gain. These values have been taken from a standard calculation I found somewhere. Path loss is 77.39 dB. Penetration loss is 22 dB. We can take it as 11 dB also if need be. Okay, depending on the system. Foliage can be 8 dB. Body block loss is 3 dB. Slow fading margin is 0 dB. Interference margin is 2 dB. Rain and ice margin is 2 dB. So we reach that beginning from 49 dBm at the transmit side, we are now receiving -77 dBm at the receive side. And if the receiver sensitivity is lower than this, then only the receiver will be able to receive the signal and communication will be feasible. On the user equipment side, if you do the similar calculation, take the thermal noise level as if we begin with -101 dBm, noise figure of 5 dB, and we calculate it. Now we find that see, this calculation is based on this the formula that has been used here. Okay, so we are considering all those factors: thermal noise, noise figure, bandwidth, and SNR. So in this you can see noise figure here. In this case, this is the SNR. Let us say the noise figure is 5 dB and the SNR is 5 dB. So when we calculate, we find the receiver sensitivity comes out to be -93 dBm, which is lower than the what we found as -77 dBm in this case. So in this case, we compare these two values, and if the receiver sensitivity is lower than the received signal, the system will be feasible, communication will occur, otherwise communication will not occur. There are some tools with the help of which you can do this calculation online also. I have got a set of tools. This is actually an open source tool. Anyone can use it. If you go to this link, you have to choose certain values. If I can show you, let me just show you. I have got it open to show it to you. I think I have to click the link. So if I use this, this is the website from where you can do the calculation. There are other calculations also. You choose this. I've taken the diagram from this only. If you choose this, you will be allowed to check whether your system with a given transmit power will be operational or not. You have to choose some input data. You can choose the cell size. You can change this thing typically here. You can change the frequency you are going to use based on the numerology of the 5G. Similarly, you can change direction, whether it is uplink or downlink. You can choose the number of blocks. numerology, you can choose whichever you want. Okay, similarly, you can configure the G node B by choosing the noise figure, the target SNIR, the cable loss. You can change all these values. You can change all these values. You can change the antenna gain of the transmit side. Similarly, when you change these values, you will get a value. Okay, so you have to just check. This is from the GNB sides. Okay, similarly on the UT side also you can change the things like what is the transmit power you are getting, the cable loss, transmit power per subcarrier, antenna gain, antenna height, all these things you can change. So when you change these things, the values will change. Similarly, you can change the path loss calculation also. You can choose a requisite model. There are so many options. You can choose one of the model and check whether that if you want to transmit a X power, whether it will be giving you a feasible communication or not. You can change the body loss. You can change the fading margin. You can change the foliage margin, foliage loss. You can change the rain and ice margin, the interference margin, and you can change the type of coverage, whether you want outdoor or indoor. You can check all these things. The results will be shown here. So if you do the calculation, you make some proper permutation combination, and ultimately if you find that the link budget is this much, and the radio, whether it is more than the sensitivity or less than the sensitivity, you will get a message pass or fail. For example, right now it is a pass, but suppose if I change the situation, I just make a major change somewhere, like for example at the GNB side, if I make some change, for example, if I make a change in the transmit power, let us do a change in the transmit power. Okay, we can do that, or we can change the cell radius. Suppose I change the cell radius to, let us say, 7,000. Okay, I'm increasing from 700 meter to 7,000. So again, I go and check what happens. So maybe I'm still getting a, actually no, there's a problem, error path. What, uh, we are having a problem here. There's no path of validity. So what I'm trying to tell you is that you can make changes in this, and you can find a optimum system for yourself. Okay, so like if you change something, maybe if you change something like, let us reduce it to 10 meter. So what happens? We can change. So all these tools are there online. You can change and you can see whether it passes or fails. Right. So let us go back to the PPT again. So I have shown this. There are two tools. Actually, both of them come from the same website. You can use this tool 5gtools.com and do your own calculations. Otherwise, you will have to do lengthy mathematical calculations for the path loss and other things. You can use these tools. But these tools also have their own restrictions. Now, in the last phase of our discussion, now we'll talk about antenna modeling in 5G communication with respect to the link budget. I told you when we began, I told you there's always a risk. People on one side always say that when you increase the network capability, when you install a lot of towers, when you increase the power output of the towers, we are always exposed to endangered electromagnetic radiations. And I remind you that phrase from blanket to bullets. So earlier we were covered by a blanket of electromagnetic wave, but now we are exposed to bullets of electromagnetic. So it is very important to consider antenna issues also. So antenna modeling in 5G involves the design, analysis, and optimization of antennas used in 5G wireless system to achieve specific performance objectives. Antennas play a crucial role in determining the coverage, capacity, and quality of service in 5G networks. And accurate modeling is essential for ensuring optimal antenna performance. This is a diagram which tells you about the placement of antenna in 5G user equipment. Although it is not a fixed one, but generally the system is like this, that somewhere you place the 4G sub 6 gigahertz antenna, you place the millimeter wave 5G antenna, you place the 3, 4. Generally, the system has backward compatibility, which means that if you buy a 5G phone, it will be compatible with 3G, 2G, 4G, all other older systems also. So we have to have different type of multi-band antennas. So this is the 3G, 4G, GPS, Wi-Fi antenna. Then we have got the 4G sub 6 gigahertz 5G antenna, millimeter wave 5G antenna 2. I told you that generally we go for more than one antenna system. So this is how we put the antenna. Now these antennas radiate a lot of electromagnetic waves. So earlier also I told you that FCC has given advisory which is saying that when you use the phone, On the display side, just after the display, you put a metallic sheet, and this metallic sheet will prevent the radiation of the antennas on the rear part of the phone by shielding and not affecting the head of the user. Okay, so it is a good practice to keep the antenna away from your head and always keep the display side towards your ear or the head, because they put the speaker in that manner. Okay, so it's a good practice, and you can avoid some radiation and get lower radiation by taking advantage of this shield. Design consideration and simulation analysis. Design consideration. Antenna design in 5G communication involves considerations such as frequency range, bandwidth, radiation pattern, polarization, gain, size, and form factor. Remember, some of the things like frequency range, bandwidth, these things are now defined. When you go for a 5G network and you choose a network system, these things are defined. So what you can do is you can control the radiation pattern, polarization, gain, size, etc. Depending on the application and deployment scenario, antennas may need to support multiple frequency bands, exhibit directional or omnidirectional radiation patterns, and be compact and low profile for integration into small cells, IoT devices, and mobile handsets. So these are some of the issues which an antenna designer has to take care of. Simulation and analysis. Antenna modeling typically begins with electromagnetic simulation, tools that allow engineers to analyze the behavior of antennas under various operating conditions and environments. Advanced simulation techniques such as method of moment, finite element method, finite difference time domain, and physical optic are commonly used to analyze antenna performance parameters such as impedance matching, radiation efficiency, antenna gain, polarization purity, and pattern coverage. We have tools like HFSS and I3D, and so many tools are there which are used for this. Antenna array design and beamforming and MIMO techniques, which are very prominent in the 5G. Many 5G systems leverage antenna arrays consisting of multiple antennas elements arranged in specific configuration to achieve desired beamforming, steering, and spatial diversity characteristics. Antenna array modeling involves optimizing the geometry, spacing, and phase amplitude distribution of individual elements to achieve desired radiation patterns and coverage requirements. Techniques such as uniform linear array, uniform planar array, and non-uniform arrays are used to design antenna arrays tailored to specific application and scenarios. Beamforming and MIMO our technologies are key enablers of 5G performance, allowing for improved coverage, capacity, and spectral efficiency. Antenna modeling for beamforming and MIMO involves optimizing the phase and amplitude of signal transmitted received by individual antenna elements to steer beam towards desired directions, maximize signal strength, mitigate interference, and enhance spatial multiplexing capabilities. Techniques such as digital beamforming, analog beamforming, hybrid beamforming, and massive MIMO are employed to achieve desired beamforming and MIMO performance objectives. Now, the effect of antenna radiation on users. You can see this very comparative diagram. On the top right side, you can see the antenna design. So when an antenna is designed using the software tools, you find out the radiation pattern. The red part indicates the power side. So when you see that, okay, radiation pattern is in the form of lobe, or it is in the form of some particular beam form. So we get satisfied, okay, now my antenna design is okay, then we fabricate it. When we fabricate it, we have to in our system. Again, we have to analyze once again. Once the antenna is put in the mobile phone, we once again analyze that which is the direction in which the radiation is going and in which direction should not. Now, in the third diagram in the lower side, you can see on the left, what will be the effect of this radiation on the head of the user, the biological effect and electromagnetic field exposure. So people have complaints. Many people complain that when they are talking or using the phone for a long period of time, they have some kind of headache, or the ear becomes warm, or maybe their face color changes, things like that. And on the lower side, in the right side, you can see this is the beam from the advanced approach in 5G. You can see 3G, 4G, sub 6 gigahertz 5G antennas. You can see there are beam formed in particular directions. Okay, so this is the uniqueness of the new technology, the 5G, that instead of having omnidirectional radiation in all the directions and wasting energy, the antenna now focus towards the user And instead of sending in 4 direction, they just focus in a particular direction. And some people call these as the bullet of electromagnetic radiation. So this is the unique technology that has made 5G very much strong compared to the older technology. However, there are biological effects and other challenges which still are to be taken care of. Now, integration and testing antenna. Integration and testing antenna involves that once antenna design are finalized through simulation analysis, prototypes are fabricated and tested in real-world environment to validate performance and compliance with specification. We use humanoid models, the phantom, to test these things. Testing may involve measurement of radiation patterns, gain, efficiency, impedance matching, and other parameters using anoic chamber, near field measurement systems, and field trials to ensure that antennas meet the design requirement and regulatory standards. These experiments are done in the microwave and other antenna labs all over India. Overall, the antenna modeling in 5G is a multidisciplinary process that combines electromagnetic theory, signal processing, RF engineering, and system level optimization to design antenna that meet the demanding performance requirements of 5G networks. It is to be taken care of that as and when there is a problem of connectivity, coverage, and signal strength, people go back to the antenna designer and they again approach them. They ask them that you have to optimize it. You have to cater to the requirement of the network. So again and again, the design has to be refined. So that is why the antenna designers are always busy with newer and newer challenges that will come ahead. They are right now working in 5G. Some people are working in 6G also. So their job is to optimize the antenna design to cater to the requirements of the network, and the requirements of the network keeps on changing. And companies, the telecom operators, are doing a lot of R&D to get advantage of the antenna design system to provide good quality of service. Accurate modeling simulation enables efficient antenna design iterations, leading to the development of high performance antennas that are essential for realizing the full potential of 5G technology. These are some of the references, although some references have not been cited. Some of them are open source references. So you can refer to these references, and I told you about the 5G tool with the help of which you can do mathematical calculations and check the feasibility of your design, check what will be the transmit power, what will be the receiver sensitivity, whether the signal will, whether the communication is feasible or not, whether it is a pass or fail. So now the floor is open. You can ask me questions, and I will be happy to answer if I can. Yes. I'm open to questions. If you have any questions related to 5G link budget design, I'll be happy to answer you.
So, Dr. Prashant Kumar, you have finished ahead of the time. I request the
Yes,
participants to put questions if you have. We have 15 more minutes now.
since this is a power link calculation, we all experience the problems in real time, and we always feel that the signal strength is not up to the required level. So if you have any doubt in your mind, anything related to personal experience related to the power link budget or signal strength, we can discuss, and I will be happy to know your problem also.
Sir, the typical two tools you have illustrated, so
Yeah.
those should be considered as a practice thing. And then
Yes.
some design parameters are to be considered.
Yes. See, actually, when we want to redesign our system, see, initially, suppose a company sets a tower of, say, cell of size 1 kilometer radius, and suppose you are facing some problem, so you can check. Now, I want to reduce the cell size, or I want to change the frequency. So instead of doing real-time calculation, which is very tough for a normal person, what they do, they use the tool. I've told you about the 5G NR tools. So you can choose this tool, and in this tool you can put the values, you can change the values, and you can find whether communication is possible or not. Okay, for example, if you change the frequency, or when you change the RB block level, or when you change the thermal noise level and other things, or you change the model. Suppose you have a model that is working in a village and you want to implement similar model somewhere else, so you can do a calculation, you can check the feasibility. Okay, so instead of going to actual calculation, which is very tough because the path loss models are very big equations and you have to take care of all the logarithmic dBm, dB, and all those things. So it is a very good tool. You can come here and you can do the calculation, and then you can be sure whether your network will work or not. You can check the feasibility of your thought process.
Okay,
You
so
can
you
play with
said
some of the parameters.
you said for undergraduate students, etc. But if some advanced thing is to be carried out, then comparison.
See, yes, see, let me tell you. See, so you know that okay, there is a design pattern and some model is there. Suppose you want to propose your model. Just think like this. Suppose you have a circular cellular region of say 400 meter and it's working fine. Suppose you out of excitement you want to know that what will happen if I increase the cell radius and make it 500 meter, or I reduce it to 300 meter. So you may get an answer that if I reduce the cell size, communication will still happen. But if I increase the cell size, maybe at the edge of the cell, communication may fail. So you can check it using these tools. Once you are satisfied, okay, that the radius of the cell can be increased, let us say from 500 meter to 700 meter, it's good. But then you will receive a complaint that on the edge your signal is not available. This is what happens when you might have seen some company, telecom company, they put their ad that we take feedback from the user and then we adopt the system and modify our system to provide better quality of service. There are many advertisements coming in the television that the telecom operator say that we take feedback from the user. They say that okay, here the signal strength was weak, then they do some modification and then they satisfy the consumer. So what they do, they actually maybe they may increase the power level, they may do some beam forming. Okay, they use the
ਹਾਂਜੀ ਇਹਨਾਂ ਦਾ ਕੀ ਕਹਿੰਦੇ
Okay, sir, there was some noise in between. So
Yeah.
what we were saying, the trial errors can help us to check it urban or rural area. But my
Yes.
question was, like, how we can go for some advanced steps? I mean, suppose somebody wants to write a research paper, or so how the thing should be taken forward?
Okay, see, just imagine, just think like this, that suppose you are interested in link power budget calculation. Okay, so you have seen there are so many parameters, and the role of a designer is to optimize those parameters. Okay, for example, there are certain things which you cannot control, like you cannot control the foliage loss, you cannot control the rain and margin. These have to be there. What you can do is that you can efficiently use the power transmitted at the transmit antenna. So maybe someone who is working at the antenna side, he can think about optimizing or increasing the antenna gain at the transmit end as well as the receive end. Okay. Suppose someone is interested in the path loss optimization. So you can think about a proper modeling. See, it is very important that when you go for a network design, and you identify what is the location where I'm going to do, which path loss model will be the best suit. And people today are see what I showed, the urban, rural, and micro, all those are standard models, but people work on modifying those models according to the changing scenarios. Okay, For example, suppose you have a metro city and all of a sudden many new buildings come into the location. So naturally that the operator will have to think about it, how to cater to that requirement of the new users and how to handle the shadowing due to the bigger buildings and all those things. You have tools like NS2 in which you can optimize, you can think about newer obstacles, you can think about network coverage issues. There's so many things you can do. And when you do that, you can use the tools. One of the tools is the PowerLink budget. You can use that tool. You can modify the channel model. Although these tools give you fixed channel model, but you can modify the channel models depending on the present condition. And again, use these tools to check whether your model matches with what the tool gives. Okay. I think you are getting my point. See, suppose you think about
Yes.
a rural urban model and you
Yes.
incorporate some newer obstacles in that environment. So you will have to change the model. You can propose a new model. Okay. And when you propose the new model, you can do the calculation on the empirical formula and all those things, and you can use the tool to compare that with your results. Okay.
Okay, sir. Got it. Thank you.
I have a question.
Yes, sir.
At what level and at what stage the link budget is calculated by whom?
See, actually, first of all, just imagine that a company has to install a network in a city. Okay. So what the company does, it goes and sees the city, takes some images and does some topographical study and comes back. The engineers who go to there, they come back and say that this is a kind, let us say, a rural macro region. Okay. And suppose they say that this rural model will suit best for it. Okay. And then they also see that there are many trees, so we have to account for the foliage loss. Okay. Then they may do some calculation. Okay, the rain is very common here, so we have to consider the rain loss. So by the time when all the observation is done, they will sit and then decide that, okay, what should be the height of the tower, what should be the transmit power, okay, what should be the diameter of the cell, that is so that all the user even on the edge should be able to receive the signal. So before the installation of the system, this kind of calculation is done. Okay. And then after that, they take the feedback from the user and they do their own feedback mechanism also, and they keep on updating their system. Like, initially they had bigger cell, then micro cell came, then pico cell, then sectorization, all these things. So in the same way, when a network is installed, initially you do the power link calculation. Okay. And you also keep in mind that in future, the mobile that will come will be naturally having more and more sensitivity because everything goes on increasing. So they just consider all those facts initially, and then the system is installed. I think I have answered your question.
Yes, sir.
But remember, power link calculation is a continuous process. The user, the operator has to keep on working on it.
But actually, in the calculation of this link budget, is there any uncertainty factor which is not included in the equation?
Okay, see, that's why we have taken the margins. Okay, we have taken the margins for that. I told you that we never go neck to neck. So if there's any uncertainty, we have to account for that, and that's why we take the margins. And a good designer would always take higher margin so that even if someone is on the edge of the circle, he or she may be able to receive the signal. Okay.
Okay, thank you.
Anyone who is interested in this kind of research in power link budget or research in the area of effect of radiation, electromagnetic radiation on human being and other biological entities, he or she may contact me because I've started researching this area some 6 years back. I've been working in the effect of electromagnetic radiation of cellular communication system on biological entities. So whoever is interested may personally contact me, and I'll be happy to share some experience and maybe provide some guideline also for further research.
Good afternoon, sir. I have one question.
Sir.
Sir, I just wanted to know whether it is possible to harness this energy, which is normally 80 watt is a good amount of electrical energy. Since I am from electrical background, so is it possible to
Right.
harness this energy for some powering up some devices like IoT
Okay.
devices or IoT sensors?
Yeah. Okay, so it's a very good question. See, the first thing is that the 80 watt, let us think like this, that it is at the base station. So you can think that the base station is like 80 watt bulb. So first thing is that the energy will go on decreasing as you go away from it. Okay, so when
Oh,
the
yes.
energy reaches you, that time it is very low. Okay, now we have a similar type of thing in which when we think of the Wi-Fi hotspots. Okay, like in some phones they have wireless charging system. So how that is working? That is working on the same concept, that the Wi-Fi hotspot, they are generating electromagnetic radiation of certain frequency, and the wireless charging equipment has got an antenna which harnesses that electromagnetic radiation from the Wi-Fi hotspot, because the Wi-Fi hotspot is very close to you. So you harness that energy and you charge your phone. You convert that into electrical energy in the battery of the phone. You can think about harnessing if you are very close to the tower. Suppose your house is very close to the tower, you can use this concept and you can harness the electromagnetic radiation of the tower to charge your battery or use it for some other IoT devices also. And let me tell you that the concept of wireless charging is based on this your query only.
Yes, I know. I have heard this that, but I was thinking that how to harness this energy. Of course, I don't have electronics background, but from electrical point of view, I was thinking in that way that whether it is
Yeah.
possible to harness this energy or not. And recently, sir, basically, sir, actually, I belong to GV Pant University of Pantnagar. Basically, it's a agriculture university. Uh,
Right.
I, I think you must have heard the name of this university earlier. Or
Yeah.
presently, sir, I'm working. We are working. Recently, we were given a problem to identify that the effect of radiation on
Right.
honeybees. So
Right.
just to mention that you are also doing some work in that area. So I think it will be good if we can collaborate on this
Yeah,
aspect further.
definitely. I will be happy to collaborate with you. Let me tell you that there are many places, especially in agriculture universities, where people are studying the effect of radiation on plants. Okay, effect of
Uh,
radiation on birds. I will like to share with you these ideas which inculcated in my mind some 10 years back. I met Professor Girish Kumar from IIT Bombay,
okay.
who was in the lead, and he was very much concerned about the effect of radiation on the environment. And he basically is a person working in the area of antennas, and he only incited this fact that told me about all these things, that the effect of radiation is naturally there. It is a matter of finding out. Although we neglect it, but if you just consider, if we can do experiment, like a very simple experiment, that if you put a plant close to a Wi-Fi hotspot and one plant in 10, you will notice the changes. So these things are, although they are slow process, you can notice this, you can study the changes, you can find out what is the ill effect or good effect of radiation. There may be some good effect also. Like if you put a plant in sunlight, it becomes green and it becomes very productive. In the same way, there may be some good effects also. So it's a matter of study.
Sir, we are also. I'm also engaged in one more study where we are
Yeah,
doing research based on different shades of the light to increase the
yeah,
productivity of the power plant. So we have
right.
increased. Right now, we have got the good results, and we have seen that the life of a flower actually can be increased depending upon the type of radiation which we are putting on the flower plant.
Oh,
So, and I think one of our PhD students is doing a very good work, and we have got some good results. So very soon we will be able to publish those results, and let us see, sir,
okay.
what exactly we get. So we are doing a good work actually in that area.
Yeah, definitely, because when you are doing the measurement, you have to do some kind of measurement of the field strength. Okay, and in that case, you need some antennas and some equipments for that to
Mhm.
standardize the results. To publish the results, you need some standards. You need to do some measurements. You can use some electromagnetic radiation meters, which are easily
Radiation.
available now. Let me tell you some. I can see on online of some very good electromagnetic radiation measurement equipments, which cost very
Mhm.
less, and you can take the reading and they give you the graph output. You can take the soft copy of it, and then you can compare the effects.
Okay,
It's
sir.
a very good
I
study. Nice to
definitely
know.
contact you as per your advice, and let's see that whether we can do further collaboration. Thank you, sir. Thank you very much, sir.
You're welcome.
So if there is no further question, it is time to thank Dr. Prashant Kumar. On behalf of FDP team and all participants, we express our heartfelt appreciation and gratitude to Dr. Prashant Kumar for his engaging presentation on this pertinent topic of optimum transmit power in urban as well as rural scenario, path loss model, link budget, antenna modeling, etc. Sir, your delivery of presentation was both informative and engaging and provided valuable insight on the subject. Your presentation was rich in content, offering clear perspective and delivering key insights to the subject matter. Your contribution as a distinguished speaker has greatly increased our faculty development program, and we all are going to benefit it. From the participant side, we also extend sincere thanks to our participants whose contribution and time are making this FDP event a successful one. And there has been a very good discussion from the participants also, and the interactive session. With all gratitude and all for all the involved, and warm regards to all. Thanks to all regards, Jai Hind. Thank you, sir.
Thank you, sir.
Thank you, all of you.
Sir, can we get Kumar sir's mail ID for further
Oh,
correspondence?
yes.
You can see
I will
my
share in
website,
the-
NIT Jamshedpur. You can just refer to NIT Jamshedpur website. You can find me in the
Okay.
Electronics and Communication Engineering department.
Okay, sir. Thank you.
I will share in the group. So tomorrow we will have two sessions. A session will be on IoT device for precision agriculture by Professor Amit Mishra, Chandigarh. And second session will be lawful interception and monitoring in 5G by Ashok Kumar sir. So tomorrow Ashok Kumar sir will be available with us. Today he has been a very engaging day. He has been in the meeting, so he could not come up. So thank you all of you. Thank you, sir.